NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will solve the cubic inequality x cubed minus 3x squared plus 3 is greater than x. We will follow a clean, 4-step algorithm. Rewrite, factor, analyze signs, and then state the solution set. Step 1. Put everything on the left. So we have a polynomial strictly greater than 0. Start with the original inequality. Subtract x from both sides. It is convenient to reorder terms for grouping. Step 2. Solve the corresponding equation to find critical points. Set the polynomial equal to 0. Now group terms to factor. Take x squared from the first pair and -1 from the second pair. Factor the common binomial x minus 3. Finally, set each factor equal to 0 to get the roots. Step 3. Use a sign analysis diagram. The factors are x minus 3 and x squared minus 1. The roots split the number line at -1, 1, and 3. First, mark the critical points. Now, consider the sign of x minus 3. It is negative to the left of 3 and positive to the right. For x squared minus 1, it is positive outside -1 and 1, and negative in between. Multiply the signs to get the product, which is our polynomial. We want the product to be strictly greater than 0. That means positive intervals only. Step 4. Since we require strictly greater than 0, we exclude the roots. Therefore, the solution is the union of open intervals, -1 to 1 and 3 to infinity. Summary. We rewrote the inequality, factored to find critical points, used a sign chart to test intervals, and selected the intervals where the product is positive. That yields D equals open interval -1 to 1 union open interval 3 to infinity. That yields D equals open interval -1 to 1 union open interval 3 to infinity. Let's write the problem clearly on screen. Step 1 is factoring. Factor out x to get x times x squared minus 2x plus 1 is greater than or equal to 0. Now notice x squared minus 2x plus 1 is a perfect square trinomial. That is x minus 1 squared. So the inequality becomes x times the quantity x minus 1 squared is greater than or equal to 0. Step 2 is to find the critical points. We set the factored expression to 0x times x minus 1 squared equals 0. That gives x equals 0, and x equals 1 from the factor x minus 1 squared equals 0. Since the power is 2, x equals 1 is a double root. Step 3 is a sign analysis. We will use a sign table for p of x equals x times x minus 1 squared across the critical points 0 and 1. The factor x is negative for x less than 0, 0 at 0, and positive for x greater than 0. The factor x minus 1 squared is always non-negative and equals 0 only at x equals 1. Multiplying the signs gives the sign of p of x. We will highlight the non-negative regions for p of x, which are at x equals 0, at x equals 1, and for all x greater than 0. To make the sign analysis even more intuitive, let's draw a number line and mark the critical points 0 and 1. We then shade the region where p of x is greater than or equal to 0, which starts at 0 and continues to positive infinity, including both 0 and 1. Finally, we read the solution from either the sign table or the number line. P of x is non-negative starting at 0 and to the right. Therefore, the solution set is the interval from 0 to positive infinity, including 0. As a final visual check, let's look at the graph of y equals x times x minus 1 squared. Notice the graph touches the x-axis at x equals 0 and x equals 1, and stays above the x-axis for x greater than 0. In this lesson, we will solve a quadratic inequality in one variable by converting it into a single rational expression, and then using a sign chart. Our problem is the fraction x plus 1 over x minus the fraction x over x minus 1 is less than or equal to 2. Step 1. Move all terms to one side, so we can compare the expression with 0. Subtract 2 from both sides. We get the fraction x plus 1 over x minus the fraction x over x minus 1 minus 2 is less than or equal to 0. Step 2. Combine everything into one fraction. The common denominator is x times x minus 1. Write each term over x times x minus 1 and combine the numerators carefully. Step 3. Expand and simplify the numerator. Expand x plus 1 times x minus 1 to get x squared minus 1. Expand negative 2x times x minus 1 to get negative 2x squared plus 2x. Combine like terms in the numerator. We obtain negative 2x squared plus 2x minus 1 over x squared minus x, less than or equal to 0. Step 4. Analyze the numerator. Consider negative 2x squared plus 2x minus 1 equals 0. Compute the discriminant, b squared minus 4ac, with a equal negative 2, b equal 2, and c equal negative 1. We get 4 minus 8 equals negative 4. So delta is less than 0, and the coefficient is negative. Therefore, the numerator is always negative for all real x. Let us also visualize this quickly with a small graph opening downward, always below the x-axis. Step 5. Analyze the denominator. X squared minus x equals x times x minus 1. Setting each factor to 0 gives x equals 0 and x equals 1. These are excluded values because the expression is undefined there. We will place these on a number line to prepare our sign chart. Step 6. Build the sign chart. The numerator is always negative across all real numbers. The denominator is positive to the left of 0, negative between 0 and 1, and positive to the right of 1. Therefore, the overall expression, which is numerator over denominator, is negative over positive to the left of 0, which is negative positive between 0 and 1, because negative over negative is positive, and negative to the right of 1, because negative over positive is negative. Step 7. We want the expression less than or equal to 0. Since the numerator is never 0, equality never happens. The negative regions occur on the intervals from negative infinity to 0 and from 1 to positive infinity. Therefore, the solution set is, open parenthesis, negative infinity comma 0, close parenthesis, union, open parenthesis, 1 comma infinity, close parenthesis. In this lesson, we will solve the polynomial inequality x to the power of 5 plus 2 is less than or equal to 2x cubed plus x squared. We'll factor the polynomial, find the real roots, and use a sign table to determine the solution set. Step 1. Move everything to the left side to put it in standard form. P of x less than or equal to 0. Then define P of x. Step 2. Factor by grouping. We set P of x equal to 0 and group the terms x to the 5th minus 2x cubed and minus x squared plus 2. Factor out x cubed from the first group and minus 1 from the second group. Now, a common factor emerges. Step 3. Factor the difference of cubes. X cubed minus 1 equals x minus 1 times x squared plus x plus 1. Step 4. Find the real roots. From x squared minus 2 equals 0, squared minus 2 equals 0, we get x equals plus or minus square root of 2. From x minus 1 equals 0, we get x equals 1. Next, check x squared plus x plus 1. The discriminant is 1 squared minus 4 times 1, which is negative 3, less than 0, with positive leading coefficient. This quadratic is always positive for real x, so it contributes no real roots. Step 5. Build a sign table across the intervals. Step 5. Build a sign table across the intervals determined by the critical points, negative square root of 2, 1, and positive square root of 2. Evaluate the sign of each factor in each interval, then multiply signs to get the sign of P of x. We want P of x less than or equal to 0, the negative regions, and the zeros. Step 6. Plot the solution on a number line. The solution comes from the negative regions and the zeros, from negative infinity to negative square root of 2, closed at negative square root of 2, and from 1 to positive square root of 2, closed at both ends. Finally, state the solution set in interval notation. Recap. We rearranged the inequality. Factor by. In this lesson, we'll solve a quadratic inequality in one variable following a clear, reliable algorithm. We want all real x such that x to the 4th minus 11x squared plus 18 is less than 0. Step 1. Factor the expression by recognizing it is quadratic in the variable x squared. We look for two numbers that multiply to 18 and add to -11. Those are -2 and -9. So x to the fourth minus 11x squared plus 18 factors as parenthesis x squared minus 2 parenthesis times parenthesis x squared minus 9 parenthesis. Thus our inequality becomes parenthesis x squared minus 2 parenthesis times parenthesis x squared minus 9 parenthesis is less than 0. Step 2. To find the critical points, set the product equal to 0. That gives x squared minus 2 equals 0 or x squared minus 9 equals 0. Solving those gives x equals plus or minus square root of 2 and x equals plus or minus 3. These four values split the real line into 5 intervals that we will test for signs. Step 3. Build a sign chart. We mark the critical points -3, negative square root of 2, positive square root of 2, and 3 on a number line. Then we determine the sign of each factor, x squared minus 2 and x squared minus 9, on each interval, and finally multiply signs to get the sign of the product. Step 4. We want the product to be strictly less than 0. From the sign row of the product, the negative intervals are between -3 and negative square root of 2, and between positive square root of 2 and 3. Since the inequality is strict, the endpoints are not included. Therefore, the solution set is the union of the two open intervals, -3 to negative square root of 2, union positive square root of 2 to 3. As a final intuition, the graph of y equals x to the fourth minus 11x squared plus 18 lies below the x-axis only between these pairs of roots. That matches our sign chart and our solution set. Great work! We factored, found critical points, built a sign chart, and read the solution. This is a dependable algorithm you can reuse for many inequalities in one variable. Example: we will solve the quadratic inequality, open parenthesis 1 minus x squared, close parenthesis, open parenthesis, 1 plus x squared, close parenthesis, less than or equal to 0. Our plan is exactly 3 steps. First, find the critical points by solving each factor equal to 0. Second, construct a sign table. And third, read the solution set from the sign table. Step 1. Set the product equal to 0 and split into factors. We have open parenthesis 1 minus x squared, close parenthesis, times open parenthesis 1 plus x squared, close parenthesis, equals 0. That means 1 minus x squared equals 0, or 1 plus x squared equals 0. Now, solve the first one. 1 minus x squared equals 0 implies x squared equals 1, so x equals plus or minus 1. Next, analyze the second one. 1 plus x squared equals 0. That would give x squared equals -1, which has no real solutions. We can also confirm that with the discriminant at equals 1 greater than 0, delta equals b squared minus 4ac equals -4 less than 0. Therefore, 1 plus x squared has no real roots and is always positive. Step 2. Construct the sign table using the real critical points, -1 and 1, to split the number line. We will make columns for the intervals, open interval -infinity to -1, then the point -1, open interval -1 to 1, then the point 1, and finally open interval 1 to infinity. For the first factor, 1 minus x squared, a downward opening parabola, it is negative outside the roots, 0 at the roots, and positive between. For the second factor, 1 plus x squared, we just established it is always positive. The product equals open parenthesis 1 minus x squared, close parenthesis, open parenthesis, 1 plus x squared, close parenthesis, so its sign matches the sign of 1 minus x squared. Step 3. We now read the final row to answer the inequality, p less than or equal to 0. We include where p is negative and where p is 0. From the sign table, that is the interval -infinity to -1 including -1, and the interval 1 to infinity including 1. Therefore, the solution set is d equals open interval -infinity, comma, -1, closed bracket, union, open bracket 1, comma, infinity, close parenthesis. We'll start with the example, and then simplify it to a standard quadratic inequality. Step 1. Simplify the inequality. Expand the left side using the FOIL method. 1 times x plus 1 times 2 minus x times x minus x times 2. Combine like terms. Move all terms to one side, so we get a standard form. Expression less than 0. Step 2. Find the roots of the associated equation. Set 3x squared plus x minus 3 equal to 0. Compute the discriminant delta equals b squared minus 4ac. Here, a equals 3, b equals 1, c equals negative 3, so delta equals 37. Apply the quadratic formula to get the two critical points. Step 3. Analyze the sign of the quadratic. Since it equals 3 is positive, the parabola opens upward, so the expression is negative strictly between the two roots. Mark the two roots on a number line with open circles, and shade the interval between them to indicate where the expression is less than 0. Step 4. State the solution set. In this lesson, we will solve the quadratic inequality in one variable. 1 minus 1 over x is less than x plus 1. We will follow a structured sign analysis approach to find the solution set. Step 1. Move all terms to one side and combine into a single fraction. We subtract x and 1 from both sides to create an expression less than 0. Then, combining the terms with a common denominator x gives us a single rational expression to analyze. Step 2. Analyze the numerator. Set negative 1 minus x squared equal to 0. That gives negative x squared equals 1, or x squared equals negative 1, which has no real solutions. Because the leading coefficient is negative, the entire numerator is always negative for every real x. To visualize this, the graph of y equals negative 1 minus x squared lies completely below the x-axis. Step 3. Analyze the denominator. Set the denominator equal to 0. That gives x equals 0, a critical point. The original expression is undefined at x equals 0, so we must exclude 0 from the domain. This point will split the number line into two intervals for a sign table. Step 4. Construct a sign table for the fraction negative 1 minus x squared over x. The numerator is always negative. The denominator is negative for x less than 0 and positive for x greater than 0. Therefore, the fraction is positive on the negative side and negative on the positive side. We are solving where the expression is less than 0, so we want the negative region. Step 5. The inequality is satisfied where the fraction is negative. That occurs for x greater than 0. Therefore, the solution set is all real x such that x is greater than 0. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.